As you can see from the title of this video, this tutorial is about resonance structures and how we draw Lewis structures for these substances that we say have resonance. If we're going to talk about resonance structures, first thing we should do is define it so that you know what it is. And a resonance structure or resonance describes molecules that cannot be accurately portrayed with only one Lewis structure. There are certain molecules out there, and we have actually worked with a couple of them already, that you cannot be completely accurate with only one Lewis structure. And the reason is because when forming multiple bonds, there are sometimes multiple sources that an atom could pull electrons from to create multiple bonds. And whenever that situation arises, what happens is it leads to there being varying structures for a substance. We looked at one earlier that was a polyion, so let's start with that one and show you what we're talking about. The polyion carbonate, CO3-2, is said to have resonance. Here is why. If I were to draw a picture of this, I would see that it's a C with an O, that's a non-metal, it's covalent. And resonance only occurs within covalent molecules. So, what I would do is I would draw my picture for it. I have carbon, which needs 4, oxygen needs 2, so I would draw carbon in the center, surrounded by oxygens. And then what I would do is add up my valence electrons. Carbon gives me 4, oxygen gives me 6, and I have 3 of those, and the -2 says to add 2 more, so it looks like 18, 22, 24 electrons. Draw your single bonds. 3 single bonds uses up 6, leaving me 18 dots to make all of the oxygens and carbon fill their octet. So start using our 18 from the outside at 1, 2, 3, 4, 5, 6. That oxygen's good. 7, 8, 9, 10, 11, 12. That oxygen's good. 13, 14, 15, 16, 17, 18. That oxygen's good. I'm all out of oxygen atoms now. Out of valence electrons now. And the carbon in the center is not happy. So here's an instance where we have to create multiple bonds. But the catch is this. I could take 2 from here and push them in, and that would make carbon happen. I could just as easily have pulled 2 from here and made this one, or 2 from here and made this one. Right? What they have found is that when they see a, say, snapshot picture of carbonate, right, that you don't see like a single double bond on the left, double on the left, and single on the top and single on the right. What they found is all 3 of these bonds are the same length, which means that sometimes the double bond, which is shorter, gets formed here, sometimes it gets formed here, and sometimes it gets formed here, and whenever we combine all those molecules together, it looks like we have 3 equally length bonds because the double bond moves. So this is one of the structures. I could easily have drawn a different one where instead of pulling the 2 electrons from here, I pulled them from the top, and that would have led me to this structure. I would have carbon, oxygen, 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 single, 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 use my 18 electrons, and instead of pulling 2 from here, I pull 2 from here, leading me to this structure. Or I could have taken 2 from this one, which would have led me to this structure. And what they found is that these structures are interchangeable. That all 3 of them exist in a naturally occurring sample of carbonate, so that no one structure is completely correct. That is the idea of resonance, when I can draw multiple pictures for the same formula, CO3 minus 2. All 3 of these are CO3 minus 2. All of them obey the octet rule. None of them, all right, is completely correct without the others. If we wanted to look at a percent abundance of each of these, if I had 100 CO2 molecules or CO3 molecules, right, and there are 3 resonance structures, 1/3 of them would look like this, 1/3 of them would look like this, and 1/3 of them would look like this. So roughly 33% would take each of the forms. Right? So that's what resonance is when we can draw multiple pictures for the same chemical formula. Let's take a look at another one. Something along the lines of SO3. Right? Sulfur trioxide is the name of that compound. Right? If we were going to draw this, you would see sulfur is to the right of the staircase, as is oxygen, right? Which means we have non-metal, covalently bond. Right? I have sulfur that needs 2, oxygen that needs 2, so we have to decide what's going to go in the middle. So we'll put S in the middle because it's the one by itself. Surround it with 3 oxygens. Work up your valence electrons. As we said, sulfur gives us 6 plus 3 times the 6 for oxygen, for a grand total of 24 electrons. Draw my single bonds. Right? That's going to take away 6, leaving me 18 valence electrons to make all the O's and the S happen. So let's try to do that. This O needs 6, 4, 5, 6. It's good. 7, 8, 9, 10, 11, 12. It's good. 13, 14, 15, 16, 17, 18. It's good. I've used up all my valence electrons. Now I have to make sulfur happy, right? Because I have no more dots to give it. Right? And again, we have reached the same scenario as we did before. Do I take the electrons and make a double bond here, here, or here? Right? And the answer is all of those. All right? So what happens is, it does not matter the order. In this one, I could make the double bond here. Right? But in a separate structure, I could have taken it from here, which would have led to the double bonded O being on the left, and a third structure where we took them from here, leading to the double bonded O being on the right. No brackets needed this time. It's not a polyatomic ion, but we do still have 3 different structures. Right? So because there's 3 structures, roughly a third of each of these will exist. So the question becomes then, because the 2 that we've done thus far were very similar, do we only see resonance come in 3s, where it can have 3 different structures? And the answer to that question is no. You can see resonance in substances that have more resonance structures, sometimes 4 or 5, right, or less, which would be 2. Right? So let's take a look at one of those. How about something like SO2? Very similar, right? But 1 less oxygen. Still covalent because it's a non-metal. So we'll put S in the middle, put an O on each side, work up our valence electrons. I get 6 from sulfur plus 2 times the 6 from the oxygen for a total of 18. Draw your single bonds. That uses up 4, leaving me 14 electrons. So we try to fill the octets. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I still have 2 left, so I'll put them on the center. 13, 14. Now I'll check my octets. Is this O happy? Yes, it is. 2, 4, 6, 8. This O, 2, 4, 6, 8. Is sulfur 2, 4, 6? No. So what's going to happen is we have to form a double bond between one of the O's and the S to get the electrons into the middle so that sulfur can use them. Right? So the question becomes, do they come from the left or from the right? And the answer is, again, both. So if we take 2 from here, one of our resonance structures will have the double bonded O there, but I could have just as easily been here, and instead of taking them from the left, taking them from the right, making the double bond there. This only has 2 resonance structures, so with there only being 2, you would have about 50% of each of those. And what they see when they take a picture is that on an overall picture of the entire molecule, you see not a double bond and a single bond of each type, but an average of it. When you kind of merge these together, they see a bond length here and here that is about 1.5. Because half of the time this is a single bond, half of the time it's a double bond. So when we look at an entire sample of it, it looks like you have a mixture of those 2 things, 1.5. So that's the idea of resonance. Right? You can have multiple pictures drawn for the same chemical formula. Right? No individual picture is correct. To draw accurately what's going on, you have to look at the entire multitude of the structures. Anytime we are working with substances, if I ask for a Lewis structure and I don't specifically ask for resonance, you could suffice with just 1. But if I specifically ask you for all of the resonance structures of a particular formula, you'll have to draw me all of them to be getting full credit for questions of that nature. I hope this helped out if you're having any sorts of confusion. If not, as always, please feel free to come in for some help.